everyone, and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over how we can find the total pressure in a reaction vessel given that we are given the partial pressures of the reactants. So let's get into this. So we have a 5.0 liter reactor vessel or flask at 130 degrees Celsius, and it contains hydrogen at a partial pressure of 3.00 atmospheres and oxygen at a partial pressure of also 3.00 atmospheres. A spark ignites the reaction and it goes to completion. What is the final pressure in the flask after it cools back down to 130 degrees Celsius? Okay, so what are some key things to kind of pull out of this problem to figure out how we're going to get the answer? So our goal is to find out what the final pressure is after the flask has cooled down and the reaction is in completion. So that means that we've produced some products. So what are the products that we've produced? We have water vapor. So in this case, we only have water vapor as a product, but we could have some gaseous substances or reactants left over because we don't know which one is the limiting reagent. So because they give us 3 atmospheres of one gas and 3 atmospheres of the other gas, well, we don't know which one's going to run out. So we got to figure that one out first. So we could have some leftover reactant that would contribute also to the total pressure along with the product formed. So we got to figure all that out. So they give us atmospheres and they give us a balanced equation. So the great thing about this is when you're given a problem like this, especially if it's a gas problem and they give you a balanced equation and they don't give you any moles, see if you can use the atmospheres as moles. And there's certain conditions under which that is going to be the case. So let's write down the combined gas law. So the combined gas law is P1 V1 over T1 N1, and that's equal to P2 V2 over T2 N2. Now, why am I writing this? I'm going to show you why you can use the atmospheres as if they were moles with the balanced equation using your mole ratios. In the same way, you can use them as pressure ratios or volume ratios. So we're told that the reactor vessel is 5.0 liters. Well, the vessel, we're not given any information about that, and we're not told that it's a flexible container. So here we can assume that the vessel is not going to change volume. So volume is going to be constant. So volume is constant. What about the temperature? Well, we're told that the reaction vessel is at 130 degrees Celsius to begin with, and then a reaction occurs, and then we're told that the flask cools back down to 130. So even though during the reaction the vessel's the temperature fluctuates, it starts at a low temperature theoretically, or seemingly it went up to a certain temperature and then came back down. That it doesn't matter if there was a change. It matters what we're measuring from and to. So here we started at 130 degrees and we end at 130 degrees. So the whatever gases are left in the container, they're at 130 degrees, just like the gases were before the reaction. So since they're at the same temperature, we can say that in a way the temperature is constant. So temperature is also constant. So in order to figure out what gas law is involved here, we are going to eliminate from the combined gas law problem or equation, we're going to eliminate the things or the properties that are constant. So we're going to eliminate volume and temperature. So V1 and V2 are eliminated, T1 and T2 are eliminated, and we're left with P1 over N1 equals P2 over N2. So what does this tell us? It tells us that whatever change in pressure, that's going to be the same change in the number of moles, right? So if I double the pressure, then I'm going to double the number of moles. If I quadruple the number of moles, then the pressure is going to quadruple as well. And I can go the other way. If I half the pressure, then I'm halving the moles. If I half the moles, then I'm halving the pressure. So what does this tell us? Why is this important? It tells us that pressure is going to be proportional to the number of moles. Why is that important? Well, that means that we can treat the pressures they gave us like moles, and we can use pressure in our balanced equation. We can treat the mole ratios in the same way with atmospheres, with the unit of pressure. So that is really important because that simplifies the problem. I don't need to convert pressure to moles and then use the mole ratio. I can use the mole ratio directly because pressure and moles are proportional. Okay, so I wanted to begin with that to kind of show you that if you look for those things, then you can simplify a problem that looks complicated to begin with. You could also do it with volume and moles too, right? So if you end up with volume over moles, V1 over N1 equal to V2 over N2, then that would tell you that the volume and the moles are proportional. So you could use volume units in the same way that you use moles. But in this problem, we're using atmospheres. So now what I can do is I can create a stoichiometry table using atmospheres. And so here I'm going to have my ICF, right? So my initial amounts, the change, and then the final amounts that I have after the reaction. So the initial is before reaction, then I have the change during the reaction, and then I have the final results after the reaction. Okay, so what do I start with? I start with 3.00 atmospheres of the hydrogen, and I have 3.00 atmospheres of oxygen, and I have 0 atmospheres of the water because no reaction has started yet in the beginning. Okay, now what do I do? Well, the next thing I need to do is I need to figure out what the limiting reagent is. And what you could do is use the ratio between the reactants to see, well, which one would run out first. And what you could do is you can convert one of your reactants, the amount of one reactant, to the amount of the other and see, well, do you have more than enough or do you have less than you need, right? So let's take oxygen, for example. So I can take 3 atmospheres of oxygen, and then I can use the mole ratio 1 to 2. So 1 mole of oxygen requires 2 moles of hydrogen to react completely. Same thing with atmospheres. 1 atmosphere of oxygen needs 2 atmospheres of hydrogen to react completely. So I can use that as a conversion factor. So 1 atmosphere of oxygen on the bottom, 2 atmospheres of hydrogen on top. So atmospheres cancel out, atmospheres of oxygen cancel out, and I'm left with atmospheres of hydrogen. So 3 times 2 gives me 6.0 atmospheres of hydrogen. So what does this tell me? It tells me that in order to react completely with the oxygen, I need 6.0 atmospheres of hydrogen. Do I have 6.0 atmospheres of hydrogen? No. So that means I don't have enough hydrogen to completely react with all the oxygen. So that tells me that I'm going to run out of hydrogen before the oxygen is completely reacted. Therefore, hydrogen is my limiting reagent. Why is that important? Well, then that's important because it tells me which one of these is going to run out and I'm going to end up with zero. So I'm going to run out of all of my hydrogen. So I'm going to lose all the hydrogen. So all the atmospheres of the hydrogen is going to run out. So I'm going to subtract, or I'm going to lose 3.00 atmospheres. So this is part of the change. This is what happens during the reaction. So I'm going to lose the 3 atmospheres. But remember, for every 2 hydrogen, I need 1 oxygen. So I need half the amount of hydrogen. So since I have 3 atmospheres that react, this is going to require 1.5 atmospheres of oxygen. So I'm going to lose 1.50 atmospheres of oxygen because that 1.5 is needed to react with the 3 atmospheres in order to form water. Now, notice there's a 1:2 ratio between oxygen and water vapor. So if I'm losing 1.5, right, then I need to gain twice as much in water. So I'm going to gain twice as much in water. So I'm going to have to double this for the water. So then this becomes 3, or a positive 3.00 atmospheres of water vapor. I could have used hydrogen too, right? So here it's a 2:2. So it's like a 1:1 ratio. So if I lose 3 of these, then that means I'm going to gain the same amount in water. And I can use conversion factors to do this too, to show you the calculations, just like I did here. Okay, now the final amount. So I'm going to add these rows together. So 3 and -3, 3 minus 3 is 0. So I run out of hydrogen gas. 3 minus 1.50 is 1.50 atmospheres. This is the pressure of the oxygen left over that was not used up. And then, of course, 0 plus 3 gives me 3.00 atmospheres. And so now I know that the final atmospheres for each of the substances. And now what were they asking for? They're asking for what is the final pressure in the flask. So to get the final pressure, we just add up all of these. So 0 plus 1.50 plus 3.00 is equal to 4.50 atmospheres total. So that is the total pressure in our reaction vessel after the completion of this reaction. I hope this was helpful. If you enjoyed this video, if this helped you in any way, then please, by all means, like the video, share the video, hit that like button over there. Also, do me a favor, subscribe to my channel, hit that notification bell. When you do that, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, if you have a topic you would like me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.